an instantaneous rate of change is going to say this. Instead of thinking about from 0, 0 up to 6, 5, and saying, okay, from point A to point B, or we'll say to point B right there, maybe your graph looks something like this. Okay, instead of saying what's my average rate of change or my average speed from point A to point B, really what calculus is going to start to deal with is say what's my speed not from one point to another, but what's my speed right then, like exactly at that one time. Okay, now this is hard because when you think about a slope, usually for a slope we need two different points to be able to calculate a slope. But what calculus is going to do is it's going to say, hey, instead of needing two different points, we're okay with just using one point. And basically what we're going to get is something called a tangent line. Okay. By the way, if I were to go back, the graph that goes through 2 points like the one we had here, if your graph looks something like this and you have a point B and a point A, the graph that goes through those 2 points, that's often called a secant line, where it kind of goes through 2 points, versus a tangent line where your graph, your line really only touches the graph in kind of that one spot right there. There's a little more technical definition, but that's kind of a general idea. Is if your line only touches your graph one time there, then this is going to be something called a tangent line. And for us, this semester, we're going to talk about an average rate of change, or an average speed deals with secant lines. An instantaneous rate of change, or an instantaneous speed, is going to be dealing with tangent lines. Okay, so then the question becomes, how do you find a tangent line if you don't have 2 points? Or I shouldn't even say the tangent line. How do you find the slope of the tangent line, which we just said earlier, a slope is like a speed. So here's what we're going to do instead. Could you calculate the slope from this point right here, I'll call that point C, I guess, from point C to point B? And just like in the last problem, I hope you would say that the answer is yes. If you knew the x-coordinate and the y-coordinate, you could do y2 minus y1 over x2 minus x1 and kind of calculate a slope that way. What about to this point right here, D? Could you calculate the slope between C and D? Again, I hope the answer is yes. And the idea of what if you have this point E, or this point F, or another point in here, G, and what's going to happen is you see these points, the points that I'm drawing, point D, point E, point F, point G, these are getting closer and closer and closer and closer to this point of point C to begin with. And so what we're going to kind of do is we're going to essentially, we're going to have a graph that says, here's one point, and we're going to have another point somewhere, but it's just going to get closer and closer and closer and closer and closer to that point, that you basically have 2 points right on top of each other. And you can calculate the slope the same way we did before, but now it basically becomes 1 point, and they kind of merge together. And so when they merge together, it kind of goes from being what we would call an average rate of change between 2 points to now turning into an instantaneous rate of change, where you're just talking about at one specific instant. Okay, think about it like this. Most of the time when you're going to get a ticket, it's not because of toll roads knowing where you are at a certain point in time and a certain point later in time. Usually when you're getting a ticket, at least here in the States, it's because a cop has a radar gun that is calculating how fast you are moving right now, like right at this instant. It's not calculating from one point to another point. It's calculating a specific value right then. Okay, and so it's kind of like using an instantaneous rate of change rather than an average rate of change to figure out your speed right at the moment. Okay, and really what it's doing is it's saying it's measuring your where you are right now, and then literally like a fraction of a second later, and those 2 points are so close together that that average rate of change is basically becoming an instantaneous rate of change. So these are kind of some sloppy graphs that I have so far. So let me go ahead and look at an example here that kind of depicts this, and hopefully this will be a little bit of a nicer graph. I'm going to give you a function to start out with. Let's look at something pretty simple, pretty straightforward, but you can do this with functions that get more complicated as well. So let's say f of x equals 3x squared plus 7, okay? And what I want to know is, can we find the average rate of change, which we already said a number of times. You should be able to do this, no problem. So find the average, I'll call it the average speed. So the average speed from x equals 1 to x equals 3. Okay. Now, I might not give you the y values, or you might not have the y values, but that's okay. You should be able to use the fact that m is, we called it y2 minus y1 over x2 minus x1 in a past class, but it should be just as fine for you to say something like f of 3 minus f of 1 over 3 minus 1. Those are the y values on top, the x values on bottom. And you can actually go ahead and plug the 3 and the 1 into your function value that you have at the beginning and find your output values. So this is 3 times 3 squared plus 7 minus, and make sure you go ahead and put parentheses there, so 3 times 1 squared plus 7, and you can go ahead and grab your calculator and figure out what you get here. If you don't want to do it in your head, that's fine, but let's see, this is 27 plus 7 minus, let's see, 3 plus 7 is 10, so minus 10 all over 2. You should get something like, what is that, 34 minus 10 is 24 over 2, so you should get 12, okay? And the idea is that this is an average rate of change because it has a starting point when x equals 3 and an ending point, or I'm sorry, a starting point when x equals 1 and an ending point when x equals 3, okay? But the idea that says, let's not look at an average rate of change, let's look at an instantaneous rate of change, kind of says this. Let's take the exact same function so we have f of x equals 3x squared plus 7, and now let's find the average speed from x equals 1 to x equals 1.1. And then once you've done that, which you should be able to calculate that, could we also find the average speed from x equals 1 to x equals 1.01, or to, so from x equals 1 to x equals 1.0001. Okay, do you see what's happening here? We're basically taking this second point, and what we're trying to do is we're trying to let that point get closer and closer and closer to the point x equals 1, so that the 2 points that we're looking at almost kind of merge into becoming the same point. Like they're so close together that you can barely even tell the difference. Okay, so let me pull up one more board here. And really what we're finding by doing this is we're trying to find f of 1.1 minus f of 1 over 1.1 minus 1. The next one was f of 1.01 minus f of 1 all over 1.01 minus 1. The third one was f of, I don't remember how many zeros there were. I think 3 of them. I think that. So f of 1.0001 minus f of 1 all over 1.0001 minus 1. And you should be able to find all 3 of these. And what you're going to see is that this is going to become a decimal value that's going to get kind of closer and closer and closer, probably to a specific number. Okay, let's see if we can find that. I'm going to do that over here. I'll give you just a second to, you can pause this video and do this on your own. And if you did this on your own, I think you should find something like 6.3 for the first one, 6.03 for the second one, and 6.0003 for the third one. And you should probably recognize a pattern here. And I would ask a question like, what do you think is going to happen if we continue to take that second point and make it closer and closer and closer to the value of 1? It would seem like these values are going to get closer and closer and closer. I'm going to put it like this. I'm going to say y, or f of x if you want. Y is getting closer to 6. You're going to get 6.000000 something. And that y value, that output value, or I tell you what, instead of using y here, which we should probably we've been calling this the average rate of change, which we've been saying is like m. So we should probably call it m. So the slope then, as that second point is getting closer and closer to an x value of 1, the slope is getting closer and closer to 6. This is going to introduce something that we're going to talk about in the next couple of sections called a limit. And there's a number of reasons why we need to talk about limits, but one of the main ideas in calculus is that it helps us be able to take these 2 points where we can find the slope between 2 points and kind of merge them into the same point, so that instead of talking about an average rate of change, we can talk about an instantaneous rate of change, so that you don't have to get you don't want to get a ticket, but so that your ticket doesn't have to just come from kind of finding one point on a toll road to another point on a toll road. We can actually figure out the speed of something moving right now. Now, I know getting a ticket is not the best kind of thought of how to or why to talk about a speed, but think about how speeds are relatable to physics, to every other part of your world. You want to be able to talk about how things are moving and how fast something is moving. When you're going into any kind of physics or computer science or related field that measures how things are changing, which is a lot of the fields around us. Okay, so that's the idea here of talking about a secant line, which is talking about the slope, or a slope of the secant line is the average rate of change, and a slope of a tangent line is an instantaneous rate of change, which is almost the same thing, but in order to talk about that, we need limits. So check out the next few sections that talk about limits as we jump into this calculus course together.